Alrighty, time to do some integration involving natural logs. The good news is this really isn't any different from a regular u substitution. If you know anything about the derivative of natural log, and if you know anything about u substitution, you could probably figure this out without the help of this video, but there are a couple techniques that we should go over, and hey, you might learn something along the way. So we proceed. Of course, we want to start by remembering that, right, integrating is just undifferentiating. So we're going to begin by doing some differentiation involving natural log. All right, so in 1 and 2, we're just going to find f prime for each function given. And of course, in number 1, f prime will be, well, the derivative of natural log whatever is 1 over that whatever. And then I have to apply chain rule, right? So I must chain on with multiplication the derivative of that inner function, which in this case would be 6x minus 2. And we'll just throw that in parentheses. And just to make things a little bit more concise, we'll say that's equal to 6x minus 2 over 3x squared minus 2x. So we could probably clean this up a little bit further, but I'm going to leave it like that for now for a reason. Okay, and so now let's go ahead and do number 2 here. In this case, f prime will be, well, 1 over the thing inside, so 1 over sine x, and then from chain rule, the derivative of the inside, which would be cosine. So, again, just to clean things up, we would say that f prime here is cosine x over sine x. Now, of course, in this case, we could simplify this and say that that's cotangent, and eventually we will. But for now, I want to leave it because I want you to recognize a pattern here. Notice, in the derivative, we are seeing a pattern, right? We are seeing some function, again, I'm going to call this u, right, on the bottom in each of these, and then its derivative on top from chain rule. So we'll say du up here. Okay, so this brings us to an important point about natural log and integration, right? If we see something that is of the pattern, right, du over u, we know that that's probably going to integrate to a natural log. So let's just summarize, right? So for example, let's say that I am going to call function f, it's going to be the natural log of some other function u. So in this case, we're going to assume that u is a function of x, right? We could just make a little note here, right? We'll just say that u is some function of x. Who cares what we call it, right? So if f is equal to the natural log of u, it is then true that f prime will be equal to 1 over u and then times du dx from chain rule, right? Because u is a function of x, therefore we must chain on the derivative of our little inner function u. And then from there, we can go to integration. So now here, let's suppose we were going to integrate the expression for f prime in the box above. So if we're going to integrate f prime with respect to x, that would be equivalent to doing, let's see, f prime is 1 over u times du dx, and then dx, right, for our integral, right? Well, the dx's, cancel, and so we're left with the integral of du over u, and we know, based on what we did in the box above, that that is going to integrate to the natural log of u plus some constant of integration. Again, we're just throwing the absolute value brackets around function u because you can't take the natural log of a negative number or 0, so it's just sort of good practice. All right, so really this right here, this is what we're looking for. If we see this pattern of a function on the bottom and its derivative on top, that's going to tell us that it's going to integrate to a natural log. All right, and we'll see how this plays out in the next couple of examples. Okay, so let's begin with example 1. Let's just zoom in a little bit here. Okay, so here on the bottom, I see a function, and then my question to myself is, if I say that this is my function u, do I see its derivative on top? Well, yes and no, but we know that with u substitution, that's not an issue, right? Technically, the derivative of u should be 2, but on top we see 1. Not a big issue. 2 and 1 are of the right order to be the derivative of 2x plus 1, so we'll proceed. So in this case, I think it's a good idea to let u equal 2x plus 1. Then we go ahead with our regular u sub business, right, and get du dx, which in this case is 2, and then we can start rewriting our integral. All right, so let's see. Let's write our integral. That's taken care of. Instead of writing 2x plus 1, I can write u. The 1 is just a 1. And then let me swap out dx for something that uses u. So let's use a little bit of algebra here, right? And then if we use algebra on this definition of du dx, you will find that dx should come out to be du over 2. Great. So by writing, well, we've taken care of the 1. By writing du over 2, we've taken care of dx because they're equivalent. All right, so really, that's just going to pull a 1/2 out, and we're left with, oh, the integral of du over u, which is like textbook. This is going to integrate to natural log. Now be careful. If you have du over root u or du over u squared, this is not going to integrate to natural log. It has to be du over plain old u. Otherwise, you've just got yourself a reverse power rule problem, which is still easy, but it's a common mistake. All right, so we know that this is going to integrate to the natural log of u plus c, and then we'll just have to back substitute because we want a final expression that involves x. So here we go, the natural log of 2x plus 1 plus c. Fantastic. Moving on to example 2. All right, we're bringing some trig into it. And so now, again, you really want to think carefully about which is the derivative and which is the parent function. It's kind of obvious here because this lesson is on natural log, so we expect u to be on the bottom, but it won't always be so obvious. All right, so in this case, we'll just try it, right? Let's say that u is equal to tan x, right? And if it doesn't work out, we can go back and try something else. And then sure enough, if we get du dx, right, the derivative of tan x is secant squared x. All right, so let's start to rewrite our integral. All right, on the bottom, instead of tan x, I can write u. And then, now here's a nice little trick that I like to use. So you can address these individually. You can say, oh, what is secant squared, and then what is dx, and solve for each of those individually and pop them in. Or you can kind of think to yourself, I need something that is exactly equivalent to secant squared x times dx. Right? If I can find something that's equal to secant squared x dx, I can just plug that one thing in. And that is a shortcut that I love. And notice, if we come down to this expression here, if we just multiply both sides by dx, we find that du is exactly equal to secant squared x dx. So we can actually just write du on top, and by writing that, we've taken care of all of this. That's a nice little trick that I like and that you can use as you sort of get more comfortable with u substitution. All right, and so now it doesn't get simpler than this. The antiderivative of du over u is the natural log of u plus c, and then we'll just back substitute and pop in a tan x for u. Done. Fantastic. All right, let's see what we've got next. Ooh, a definite integral. Fancy. All right, so that's not going to change how we begin the problem, right? We still need to get the correct antiderivative. And so now we see a couple things happening, right? Do I see a function and its derivative somewhere? Yeah, I see an e to the x and its derivative, e to the x. And so then you're like, well, do I call the thing on the bottom u and the top is du, or do I call the thing on the top u and the bottom is du? I would be careful and just sort of remind yourself that when you do an integral, right, your dx or du or whatever, it's always being multiplied in. So we don't want to have a du in the denominator, right? So in this case, I think that we should choose u to be the entire denominator, right? And what's nice about that is if we let u equal this whole thing on the bottom, we get rid of the 1 as well. But you know what? You could try it. You could try it the other way. It probably wouldn't work, or you'd get stuck somewhere, and that's fine. You just start over. Oh, maybe I needed to choose u differently. Okay, again, integration techniques. Anywho, all right, so if u is 1 plus e to the x, then the derivative of function u with respect to x is e to the x. So let's start rewriting. Okay, so I'm going to do my integral. I'm going to save my limits of integration because I need to change those. At least that's how I like to do it. And I'm just going to start to rewrite the integrand. All right, so on the bottom, instead of 1 plus e to the x, I'll have u. And then on top, I'm going to use that trick again, right? I need something that is equivalent to e to the x dx. And then here comes multiplication, saving the day. Oh, look, by writing du, I will have taken care of both e to the x and dx. So let's throw a du on top. That is a terrible du. You know what? I'm actually going to even take the time to undo that. du. Okay, it's better. All right, so the denominator's been taken care of. The entire numerator's been taken care of. Now I need to fix my limits of integration. All right, so I would just prefer to have u values in my limits of integration since my integrand is in terms of u. Okay, so from here, let's do some stuff. All right, when x equals 0, let's see, well then u equals 1 plus e to the 0. So that's 1 plus 1, which is 2. Great, so instead of x equal to 0 here, I will plug in a corresponding u equal to 2. And then let's do the same for x equals 1, our upper limit of integration. So then u would equal 1 plus e to the 1, which is going to work out to be 1 plus e. All right, she ain't pretty, but she'll do. All right, so now let's go ahead. We've got a very simple integrand, right? This is going to evaluate to the natural log of u. Since it's a definite integral, we don't need a constant of integration, but we will have to evaluate it from 2 to 1 plus e. Alrighty, so let's do the definite integral. We'll have the natural log of 1 plus e minus the natural log of 2. And I can just drop the brackets there because the natural log of 2, right, well, 2 is just positive anyway. All right, so now let's do some work on the natural log of 1 plus e. Can we simplify that at all? I don't think we can. In any case, the quantity 1 plus e is going to be positive, right, because e is 2.71828, so on and so forth. So we can leave it like this, and then if we wanted to make this a little bit more visually appealing, we could use one of our log properties. I'm going to write it here on bottom that says that the natural log of a minus the natural log of b is the same as the natural log of a over b. So let's do that. We'll say that it's the natural log of 1 plus e over 2, and I'm happy with that. Pretty easy, right? I think so. It's not too bad. It's just a regular u sub. Of course, it can't just be that simple, right? There are going to be some times when you have an integral that actually does go to a natural log, but it doesn't look like it goes to a natural log. All right, and so that's what we're going to address on the next page. All righty. Here we go. So here's an integral where if we look at the denominator, right, we've got x squared plus 1, so the derivative would be of the order of, x to the first. So we definitely do not have function on the bottom, its derivative on top. And yet this will end up becoming, or at least involving, natural log when we integrate it. All right, and the trick, as you might have guessed, given the title of this page, you clever, clever student, it involves using long division to sort of untangle this and chunk it up a little bit. Alrighty, so let's just see what happens when we do use long division, and then we'll talk about, strategy and how would you know when to do this and why. All right, so if you remember your polynomial division, oh, I hope you do. All right, let's put our divisor outside the house. And then our dividend, hello, 4th grade, welcome back, inside. Okay, and let's do our polynomial division. X squared goes into x squared once. Then we will multiply everything. Okay, so 1 times x squared is x squared. And then 1 times 1 is 1. All right, so I'm going to put that over here with the 1s. All right, and then basically we have to subtract, and the catchy little phrase that I like to use for this is draw the line, change the sign, then combine, right? Because changing the sign, that's the same thing as subtracting, right? Multiplying in a negative. All right, so 1 plus negative 1, that gives me 0, right? X squared minus x squared, and then x minus nothing, that's just x. And then we have to stop, right? Because we can't do x squared into x. So then the trick becomes, how do we rewrite this integrand, right, using our polynomial division? Well, think about, if, I know we shouldn't really be doing like a polynomial division lesson right now, but why not? All right, think about what happens when you do a simple division problem like, I don't know, 5 into 48. All right, so you'll do 5 goes into 48, wait, what's that going to be, 9 times, right? And then 9 times 5 is 45. Draw the line, change the sign, then combine, and you get 3. So you would say that the answer is 9 3/5, which is really the same thing as 9 plus 3/5. So that's exactly what we're going to do here, right? So in this case, our answer was 1 plus, and then remainder over divisor. So x over x squared plus 1. All right, so let's rewrite our integrand now. So we'll have 1, try try that again. Okay, a little better. 1 plus x over x squared plus 1 dx. And really now we can just take this term by term. All right. The 1, that's easy enough to integrate. You could split this up into 2 integrals if you wanted to, or we could just remember that the 1 is there. All right. But now if we look at the second term right here, we do see that pattern of function on the bottom and its derivative on top, right? X is of the right order to be the derivative of x squared. All right, so let's go ahead. I'm just going to do a u sub for this term that I've underlined in blue, but we will not forget about that plus 1. All right, so in this case, we'll let u equal x squared plus 1, which means that du dx is 2x, and so now we will start to rewrite. Okay, and at this point, I actually am going to split up these 2 integrals. Why? Well, because the piece in blue we have changed to u's, but the 1 we have not, and so I don't want to mix those up. So here I'll have the integral of 1 dx, which is, I'm just going to say dx, and then plus, all right, now the integral, oh my goodness, the integral, hey, for which I have done this u sub. Okay, fine. All right, so on bottom, I have u. Alrighty, so great. And then on top, all right, really I just need something that is equivalent to x dx. So I'll get that from here, right? So I can see that du is 2x dx, therefore du over 2 is exactly equal to x dx, and that's what I'm going to use. All right, so actually I think I'm just going to put a 1 over here, and then I'll do like times du over 2. Great, fantastic. All right, so we've done our u sub integral. We've left this 1 out on its own. Great. All right, so then, well, the antiderivative of dx is x. And then this, right, since there's a 1/2 in there, it's just going to be a 1/2 on the outside, and then it's going to go to the natural log of u plus c, right? And that plus c can account for both integrals because one constant plus a different constant is just some other constant, so we're not going to fuss about it. And so then let's just back substitute to get everything in terms of x's. So you'll have x plus 1/2 the natural log of x squared plus 1, and then, plus c. And you could really even drop the absolute value brackets because the quantity x squared plus 1 will always be positive. So, you know, I'm just going to like write this final answer down here where I have a little bit more room. Your final result should be x plus 1/2 ln x squared plus 1 plus c. Yeah, it's a sad little n there, but there you go. Okay. Right, so really, by using long division, we were able to turn this, I've now, of course, scratched it all out, into a mixed number, fundamentally, right? Or like a mixed expression, where the first part's a nice whole number, just like was the case with this 9, and the second part's the fraction, right? And so then we were able to split it up into 2 terms and integrate each separately. This just became regular power rule. And the fraction part ended up being the natural log part. All right, so that's just a little sort of overview. And usually, all right, now let's talk technique, all right, and strategy. The long division is something that you will attempt when you notice that, okay, we'll just write this in here, that the degree of your numerator is equal to or greater than the degree of your denominator. So let's just write that down. This is something that we would attempt when the degree of our numerator is greater than or equal to the degree of the denominator. Because if the degree of the top were less than the degree of the bottom, this would probably already be a candidate for natural log integration, right? So in that case, we would just go ahead. All right, let's try another example. Okay, it's a definite integral. Not a big deal, right? In this case, the degree of the top is greater than the degree of the bottom. And, you know, it's a rational expression, right? Polynomial on top, polynomial on bottom. So nothing jumps out at us right away. We could try factoring the top and canceling, but ultimately I don't think that will work. So we'll attempt to use a little bit of long division and express this one rational expression as a mixed number instead of an improper fraction, basically. Alrighty, so let's do our long division. So x plus 5 is going into x cubed minus 6x minus 20. All right, so x goes into x cubed, x squared times x is x cubed. X squared times 5 is 5x squared. All right, and so then draw the line, change the sign, then combine. Well, x cubed minus x cubed goes away. Technically, right, I should have put a little placeholder in my dividend, right? It's really like 0x squared minus 5x squared. So that'll be negative 5x squared, right? And then we can just bring everybody else down. So negative 6x minus 20. And then we can go again. We can say x goes into negative 5x squared, negative 5x times, then multiply. So we would get negative 5x squared down here. And then that's going to be negative 25x. Draw the line, change the sign, then combine. This will give us a positive 19x. Cancel, cancel. Bring the negative 20 down, and we can go again, right? X into 19x goes 19 times, so we'll have 19x, and then 19 times 5. Let's see. Well, 20 times 5 is 100, so 19 times 5 is going to be 95. Okay, so then draw the line, change the sign, and combine. Goodbye, goodbye. And then that's going to be negative 115. Man, it's always the simple math, isn't it? Okay, so now let's rewrite our integral as a mixed number. And ooh, it's a definite integral. Okay, so we'll have from 1 to 2. And then let's see, so we're going to have the whole thing, right? Our whole number part, which was up top, x squared minus 5x plus 19, and then plus remainder over divisor. So really, the remainder is negative, so we'll have a negative 115 over x plus 5 dx. Okay. And now, all right, when we do the definite integral, the first three terms are easy. The second, or I'm sorry, the last term will require some natural log, but let's just start hitting it one by one. The antiderivative of x squared is x cubed over 3, and then this will be minus 5x squared over 2 plus 19x. And then here, you can do the u sub for this term. You'll start to get a handle on shortcuts that you can take. So for now, I'm just going to leave you with, oh hey, this antiderivative is 115 times the natural log of x plus 5. And oh my goodness, I'm out of room. Just pretend that I closed my brackets and put my limits of integration on the end. Okay, so now let's evaluate. So we're going to have, let's see, 2 cubes, so 8 over 3 minus, is that going to be 20 over 2, so that'll be 10, plus 19 times 2 is 38, minus 115 times the natural log of that was x plus 5, so that's going to be the natural log of 7. And then minus this whole thing evaluated at x equals 1, so that will be 1/3 minus 5/2 plus 19 minus minus 115 times the natural log of 6. Okay, and I'm not going to get bogged down in those calculations. You can do fraction math, you can take it to your calculator. You could even, since it's a definite integral, just take this whole thing and use your calculator and confirm the answer that you get by hand. But the difficult part is done. Alrighty, so last but not least, on the next page, we want to see how knowing how integration with natural log works, we can start to get at some integrals and antiderivatives of trigonometric functions. Alrighty, here we go. Alright, what's the antiderivative of tan x? Well, we know the derivative of tangent. We know some derivatives that involve tangent. For example, the derivative of secant x is secant x tan x, but you know, that like if this were what's the antiderivative of secant x tan x, we'd be in business. But this is not that. So the trick here, and again, how would you know how to do this? You wouldn't necessarily, right? I'm going to tell you, and hopefully you sort of start to see these opportunities with experience, right? But if we rewrite tangent as a quotient, right, we're going to start to see a nice little familiar pattern. All right, so let's, instead of writing tangent, let's write tangent using its identity of sine over cosine. And now we ask ourselves, do we see a pattern of function and derivative? And the answer is yes, but we need to be careful. I think most people like to say that u is sine because we're like, oh, u is sine and then du dx is cosine, which is fine, but remember, we don't want a du on the bottom, right? We're always multiplying by dx or du or dy or whatever because an integral represents area, which is length times width, not length divided by width. So if your choice for u results in a du on the bottom, again, you might want to rethink it. All right, so armed with that knowledge, I'm going to say that u is cosine of x, which will make du dx equal to negative sine x. And that's okay, right? The negative, that's not a big deal. It's the sine part that's important. All right, so let's start rewriting. I've got my integral. And then on the bottom, I can write u, which takes care of this. And then I would love to have something that's exactly equal to sine x dx, and we'll get that from here. So du is equal to negative sine x dx, therefore negative du must be equivalent to sine x dx. All right, so I will write negative du up here, which takes care of everybody here. Fantastic. All right, so really this is just, right, a negative outside, and du over u, that's a recipe for the natural log of u plus c, and then we will back substitute. So u was cosine x. Great. So this is something that you're going to want to put on your antiderivative sheet, that gold sheet that I've given you, right? The antiderivative of tan x is negative natural log of cosine x plus c. All right, let's do another. And I think this might be the last one. All right, so is it the last one? Yes, it is. All right, so here we go. Antiderivative of secant x. All right, I hate to tell you, you're not going to like me for this one, but it's going to be okay. All right, it's not difficult. It's not difficult. Just there's a step that is not obvious. All right, so to do this, right, you could probably guess that what we want to do is express secant as a quotient, right? And we know that secant x is the reciprocal of cosine. However, this doesn't really help me in terms of like the function derivative pattern, right? 1 is not the derivative of cosine, so that doesn't really help me. All right. Yet we still want to get a quotient because, right, things that go to natural log look like quotients. All right, so here's where the tricky step comes in. And again, this comes with experience, right? Somebody figured out that you could do this, and eventually, after enough of this, you would start to figure out what the intuition for doing this is. All right, so we've got secant x, and what we're going to do is multiply in a secant x plus tan x on top, but like we can't just do that, right? We have to do the same thing on bottom as well, so that fundamentally we're multiplying by something that's equal to 1. Great, dx. All right, and then from there, let's simplify and see what we have. This will give us secant squared x plus secant x tan x all over secant x plus tan x, and then of course dx. All right, and now it's sort of like, all right, so how did that help us? I'm not sure that I'm any better off. All right, and it's okay. We are. All right, we've just got to kind of proceed methodically, I would say. And that's because if you take a look at the bottom, right, again, what was the whole purpose of this, right? To get the function derivative pattern, a du on top and a u on the bottom. So let's check. Let's just check and see where we are before we freak out. All right, so we're kind of hoping that this can be our u. All right, so let's see. If we define u to be secant x plus tan x, let's see what du dx works out to be. Well, the derivative of secant x is secant x tan x, and then the derivative of tan x is secant squared x. And oh, look at that. Everything's fine, right? If the bottom is our u, then the top is our du, and we can keep going as normal. All right, so let's start to rewrite. All right, I'm going to come up here. Let's just divide this in half. Okay, and so then our integral will be, all right, and so now I will put my u on the bottom, which takes care of this, and then I need something that's equal to secant squared x plus secant x tan x all times dx, which again, I can get from this definition right down here. I'm not going to write the whole thing out. I think you kind of get the hang of it. Du is exactly equal to all of this times dx, right, if you multiply both sides of this by dx. So I'm just going to write du. All right, and so that takes care of this entire mess right here. Isn't that lovely? All right, and so then the antiderivative of du over u is always the natural log of u plus c, and then last but not least, we'll just back substitute to put everything back in terms of x's. And so in this case, u was secant x plus tan x plus c. Okay, so this is another one that you're going to want to put in the gold sheet. In fact, you should be able to fill in now antiderivatives for all 6 fundamental trigonometric functions. You should have antiderivatives for sine, cosine, tangent, secant. You can do similar proofs to figure out the antiderivatives, right? To figure out the antiderivative of cosecant x dx and the antiderivative of cotangent x dx. But remember, there was a relationship for derivatives between a function like secant and then cosecant, and a function like tangent and cotangent. So there will be a shortcut, right? Really, if you memorize this, you'll know this one. If you memorize this, you can easily get to this one. So you could try to prove them on your own, or you could just look them up and see what the pattern is. But I recommend that you try them just to get some practice with the U substitution. All right, so that's everything that we need to know for U substitution that goes to a natural log. Again, the more you practice, the more steps you'll be able to do in your head and skip, and you'll sort of get a rhythm to it. But while you're learning, show your work. Alrighty, happy calculus.